Page replacement algorithm is very important for effective virtual memory management, and this project will be showing first in, first out, and least recently used algorithm with a real-world scenario that is the chef analogy with coding simulation. In modern operating system, virtual memory allows us to run program larger than the physical memory by loading only the needed page into RAM. But when the memory is full, the system must choose which page to swap out. This is where page replacement algorithm comes in. FIFO, or first in, first out, means to always remove the oldest page in memory. However, FIFO can lead to more page faults because sometimes the oldest page is still heavily used and causing what's known as Valdez anomaly, where more allocated frames can lead to more page faults. LRU, or least recently used, means to remove the page that haven't been used for the longest time based on the assumption that page used recently are more likely to be needed again soon. This approach generally reduces page faults compared to FIFO and keeps the system running more smoothly. There are two ways of implementing LRU, which is by counter or by stack. In this project, we use the analogy of a chef using FIFO and LRU to replace the seasoning bottles on the table. Seasoning bottles represents the page, prep table represents physical memory, where shelf, where the bottles are initially kept, represents the back-end store. The chef has to decide which bottle to swap out to keep cooking efficiently.
Now I'll be presenting the methodology of our project. In this project, our group focused on simulating the virtual memory management through two common page replacement algorithms, which are first in, first out, and least recently used. The objective was to visualize how pages are replaced when memory is full by two different algorithms and using a trace table to record the result, and then we analyze it. So in our project, we have 5 main phases. The first one is conceptualization. We define the project goals and objective here. After that, the second phase is design. We build the memory structure, trace table design, and program logic needed. Then, implementation phase. We code 2 separate C++ programs for FIFO and LRU. After that, the fourth phase is testing. We validate both programs with the same reference string to ensure the correct memory updates and page fault tracking. Finally, the last phase is the analysis phases. In these phases, we evaluate and compare the total number of page faults produced by each algorithm to understand their efficiency. So next, the hardware and software requirement. There is no special requirement for hardware, just use standard personal computer or laptop to run the simulation. For the software, we use C++ compiler and Visual Studio Code for development. These are our task distribution. Our group distribute the work equally among the group members. Now I'll be explaining the design and implementation section in our project. For the system design, we have 3 main components, which are input, processing, and output. The input is the page reference string. The processing, since we have 2 different algorithms, so we will have FIFO and LRU here. Then for the output, this result will be printed in a table. Let's move to the system flowchart. So this is our system flowchart, and the flowchart clearly shows how the system works. From start, convert the reference string to integer. Then we read the page from the reference string converted just now and check that is there page in memories. If yes, just print memory state and fault status. If no, we need to choose which algorithm to apply, FIFO or LRU. Then after apply the algorithm, we update the memories and page fault counter. After that, print memory state and fault status. And when we completing this all, we need to know that are there more pages? If yes, return back and repeat the process here. If no, just display the total page fault and end. Then for the code implementation, for the FIFO implementation, the first step is initialize simulation environment. We initialize the reference string, frame, and the vector. After that, convert reference string to pages. Then we check the page present in memory by using this code for loop. Then we apply FIFO replacement logic here. And finally, print the memory state and page fault. For the LRU, is almost the same like FIFO. but just slightly different. So first step is initialize simulation environment. In this case, there are two vectors, then convert reference string to pages, like just now, and update frequency on page head using this kind of code. After that, we will apply LRU replacement logic here, and finally print memory state and page file.
Good day, now I'm going to be presenting the page replacement using code simulation. So we are implementing it using C++. So let's first run the code. So here is the output for the first in, first out. We have print the header. The string is this one, and then the number of frames is 3. We have traced the requests for each of them, and then memory of each request, and then is there a page fault? And then we have calculated the total number of page faults. Let's have a look at the code. Here is the initialization. We have initialized the reference string, and then we would place this reference string inside to these pages vector using this for loop. And then we initialize the frames to 3, and then we initialize the memory with 3 slots, with each of them would be -1. And then the number of page fault would be 0 to calculate the cumulative number of page fault. Here's the implementation. We are using two variables to help us during the FIFO implementation. First is the current index, which is initialized as 0. This current index is going to trace which one is the first in that shall be replaced in the next iteration. And then for available is the helper for us to see if the request is inside the memory or not. So we are going to go through each page one by one to check if the page is in the memory. So if it is not available, we're going to add it into the memory. We're going to check, we're going to initialize each time so that available is 0 first. And then when we check, we are going to go through the memory one by one. So if it is equals to the request, we are going to flip the value of available to 1, and then we are going to break out of this for loop. So it is available. We are not going to go into this side. We're going to print the trace table. But if it is not available, we're going to add it to the memory. So first, if it's not available, we're going to increase the page fault by 1, and then we are going to replace it with the current index. That's what I mentioned just now. So the current index is initialized as 0, and then if it's not available, each time we replace 1, we are going to add the current index by 1 over here. So let's have a look at the trace table. So here are the initialization as I mentioned previously, and then the current index is 0. Okay, so this is how it looks. At first, we are going to request for page 7. We are going to check through this memory, and it is not available. So we are going to add it to index 0. So as the current index is 0, right? So we're going to add it to 0 here. And then page fault increased by 1, and then we will increase the current index by 1. So next, the page request will be 0. So it is not available. So we are going to replace it inside the memory. At the current index 1. There's page fault, and then we're going to increase the current index by 1. So it becomes 2. And then as we go on to page 1, it's not in the memory. So we're going to add it to the memory, and then the index would become 0 because we have the modulus number of frames over here so that it will not exceed the number of frames. And then the page number 2 is not available and is going to be placed in the index number 0. So when we go on to the next one, which is page 0, we have found out that it is available inside the memory. So we are not going to change anything. We are just going to proceed. So the current index is also not changed because if it is available, we do not enter this if statement over here. So the page fault also does not increase, and then we move on to page 3, it's not available, and then we're going to replace the current next one. And the current index is going to be increased to 2 for the next one. We are not going through all because it's too much. Next, we're going through the LRU, the list recently used. Let's run the code. Okay, so here's the table for the LRU, like the one we traced as previous one, and then total page fault is 12. So again, let's go through the code. It's almost similar for the initialization. It's just that we have added one variable to check the frequency. So we're going to have each of them initialized to 100. We need to make sure that this initialized number must be greater than the number of frames up. And then let's go to have a look at the implementation. We have added one variable over here for the frequency, and then we have also reduced one variable, so it doesn't keep track of the current index right now. We still have the boolean for available to check if it's available inside the memory. Again, we're going to go through each of the pages and check if it's available in the memory. If it is available, we are going to again flip the boolean to available, and then we are going to re-initialize the frequency of that memory. Like it is a parallel vector over here. So this memory and frequency, they're actually parallel. Yeah, we are going to initialize the parallel frequency to 0, and then we're going to add all the frequency by 1. Over here, if it is not available, we're going to increase the page fault as usual, but then we're going to have one max index. So we're going to check which one is the least recently used by checking the less frequent one. So because we are going to add the frequency, right, every time that's available or not available, so this is where we use it. So we're going to get the frequency number, which is the maximum, and we are going to replace the memory of the maximum index, which is least recently used, by the current page that is being requested. Again, we are going to initialize that frequency to 0, and then again we are going to add each of them by 1. After that, we're going to print the trace table out. Let's have a look at this, how the frequency works. So this is the initialization, which is similar to the FIFO one. It's just that we have added one more variable, which is the frequency. So we initialize them as 100 at the first place, just an arbitrary large number. The pages over here, for page 0, it is not available inside the memory. So we are going to put it to 7. So how did we get 7? It's by this maximum index over here. So we're going to go through the frequency and see which one is the maximum. We are using this one if it is greater than. The greater, it will get index 0. throughout this, and then so it's going to put 7 inside index 0, and then we're going to update the frequency to 0. Yeah, sorry, and then we are to 0, and then we are going to increment it by 1, right? So that's what is done over here. We are going to initialize it to 0, and then we're going to increment each of them by 1. This is here some mistakes. Okay, so it's going to increment it by 1, and then for 0 it is not available. So we're going to go through this frequency, and then we found out that it is index 1 which is the greatest, so it's going to replace at index 1 over here. And then again we are going to initialize the frequency of index 1 to 0, and then we are going to increment it by 1 for each of them, so you get this frequency at last. And then for the next request, page number 1 not available also, we're going to go through each of them, and we found out that this is the greatest, so it's going to replace it at this index number 2. So for 2 also, if we go back and we found out that 3 is the greatest and replace at index 0, and then for 0, since it is available, we got it that is available at index number 1. So we are going to initialize it, the index number 1 to 0 first, and then we increment the entire frequency by 1. So that's what is done over here, where we're going to initialize this to 0 first, and then we're going to increment each of them by 1. So that's the result. They get the frequency, and then for 3 it's not available, and we get the least frequently used is the last index, and we updated the frequency. So that's all for the code implementation.
For result and discussion, we use the same page reference strings with 3 page frames to compare the performance of first in, first out, and least frequently used. And figure and here show the set of memory state for each algorithm. Here is first in, first out, and here is least recently used. As a result, you can see from here, first in, first out result in 15 page faults, while least recently used has only 12 page faults. This means that least recently used perform better than first in, first out for this case. To help understand this, let's imagine a chef working in a busy kitchen. The chef only has a space for a few seasoning bottles on the prep table, but has a longer collection on the shelf. If the chef uses first in, first out, he removes the seasoning that has been there the longest, even if it still needed. This could slow him down when he has to go get it again. But if the chef uses least recently used, it replaces one he didn't use in a while, keeping the most frequently used ones nearby. This helps him cook more efficiently. In the same way, first in, first out doesn't consider how recently a patch is used, so it can replace important patch too soon. Least recently used keep track of which pages are used more recently, so it avoids replacing pages that are still useful. So here is some ways it suggests for the further development. Assign to more frame size so that more patch can be inside the algorithm. And second is development GUI to allow dynamic visualization, memory frame operation, and faults. And lastly is measure additional metrics like hit rate, execution time, and memory users to analyze algorithm efficiency from multiple perspectives. In conclusion, this project helps us understand how virtual memory is managed using first in, first out, and least recently used. By writing the simulation in C++ and testing with the same page reference string, we saw that least recently used gave better performance than first in, first out. Even though first in, first out is simple, it doesn't consider how recently a patch was used, which can cause unnecessary patch fault. Least recently used, on the other hand, keeps frequently used patch in memory longer, which makes it more efficient. Through this project, we also learned how to apply a real-world analogy, like a chef managing limited seasoning space, to help expand operating system concepts. Lastly, we would like to thank Dr. Zafrans and Dr. Talami for their guidance and support, and also thanks all our group members for supporting each other during this project. Everyone gave their best efforts and worked well as a team. And here is a reference that I used in this project. Thank you, everyone.